Okay. Let's get started again. We've got a lot of ground to cover here yet. We're finishing up with forces, or the force methods, chapter 6. And there's several of these things. We had circular motion that we looked at. There's also resistive forces, where this idea of friction is more complicated. And it's even more complicated than these. But let's get started with these basic simple models of these resistive forces. One where the resistive force is proportional to the velocity. We say R, resistive force, would be some proportionality constant we'll call B for this. And the idea is when some object, let's say we're going to take a drop of ball or something, and it's going to, let's say, start from rest, and we're just going to drop it. It's going to start to accelerate. As it picks up speed, that wind resistance is going to fight that and is going to want to pull back. And so as it's coming down and building speed, this resistive force keeps getting bigger. At first it started off, it was just going to fall with mg, and so initially it starts to accelerate at 9.8. It does pick up speed, but again, now this resistive force starts to kick in, and it's going to start to slow it down a little bit. But as long as the weight is bigger than this resistive force, it will continue to pick up speed. And as it picks up speed, the resistive force builds more. And at some point, this resistive force is going to equal to the force of gravity, and then the net force is zero, and there'll be no acceleration, and it stays at a constant speed, and that's what we'll call the terminal velocity. So V becomes what we'll call V sub t, terminal velocity. That's where the resistive force is equal to mg. We can look at this. I'm calling down positive in this case, simply because obviously it's going to fall in this direction. Mg minus bv has to be 0, or the terminal speed is going to be mg over b. So this basic picture, in some problems, this is about all you need to know to answer these kinds of questions. As long as it's at these kind of extremes where it is at terminal velocity, this is a fairly simple answer. If we want to go back and say, well, let's get the velocity as a function of time, then we back up, and the idea that we have at some intermediate here between where we start and when we hit terminal velocity, where the resistive force is less than mg and the thing is still accelerating, we can start to take a look at this. Now, I'm not going to, I've got a lot of stuff here, so don't get too scared. I'm going to tell you what's going to be important for you. The idea of F equals ma, the net force, and we would look at the net force here. Again, I'm calling down positive, so it's mg minus bv should equal ma, but a is just dv dt. Now the idea is we want to solve for velocity, but we've got a problem here. We've got the derivative of velocity as well as the velocity. This is a differential equation, which some of you have maybe had, most of you haven't. Then what we want to do, like we would do in any kind of equation, you want to solve for something, you want to separate variables. You want to get maybe velocity on one side of the equation and time on the other side. In this case, our time is tied up as in the differential form, so it can come out over here. And I've got dv here, or mdv, and I'm going to take all of this and divide it. So this is what we call our separation of variables. I have this. And then the idea is if we're going to fall, we're going to be integrating. In some little time delta t, there's going to be some change in velocity that's going to cause a little bit of a change in distance or displacement. And we would need to integrate these things as we fall. So take and integrate both sides here. This one is related to time. That's going to go from 0 to some time t. And the velocity, we're starting at rest. So that velocity here is going to be 0 and go up to some final velocity. So hopefully you can kind of get this picture. This isn't too difficult, although it is kind of stretching kind of your use of calculus, but it's good in that you get a chance to see this. Now, doing the problem, this is a bit of a problem with calculus. Basically, at this point, it's now a question of doing the math. When we have this, it would be useful if you're going to say, hey, I'm going to do this integral. You probably want to use a u substitution, so you could do that. We're also going to need to, if I'm going to do a u substitutions, I need to change dv into a du. I'm going to not get too caught up in the details. The pieces are all here if you want to go ahead and piece this together. This just integrates to being t. I took this minus mb over to the other side. And then this would be du over u, so that's the natural log. I have to adjust these limits, so those of you that know how to do this, do this. If you haven't seen it before, it could be interesting in just trying this. Then the idea is once we have that and simplified, we take e to this power, e to that power, and we take e to this power, but with the properties of logarithms, that they're just inverse functions that just brings back what's inside here. And then it's a matter of just now solving for v, and we can get the velocity is equal to mgb over 1 minus e to the minus b over mt. And so now we have velocity as a function of time. Something that's good to see, this mg over b. Oh, we saw that over here when we dealt with terminal velocity. Mg over b is the terminal velocity. So instead of writing that, I can write the terminal velocity. You may want to store this equation in your head. He has sometimes asked questions with this. I don't think he's not going to ask you to derive this. I've kind of outlined it here because I'm going to show you next a problem where he would expect you to, in spirit, do what we're doing here. Enough on that in just a minute. But the idea that you have this, you may want to look at some of the, there's a couple homework problems, several, that deal with using this equation. I think you want to review those. We're kind of limited on time here, so I think I'll just kind of point this out and point you towards your homework as far as seeing what's happening here. Most of it is just plug and chug, and when he has done this in the past, it's been pretty straightforward as long as you kind of remember the equation and the basic ideas. So again, we're kind of run a little behind, but let me do what he has been doing, and so this better get your attention. He's been doing this type of problem again and again and again in different forms. He sometimes has a pitcher throwing a fastball towards the batter, and it's related to a resistive force, and this resistive force is going to be proportional to the square of the velocity. Okay, we've talked about all kinds of different relationships. This is one. Probably most of these, there's a combination between proportional to and proportional squared and even maybe higher order terms. But we're going to play with a resistive force that he says is going to be 0.61 times v squared. Units are going to be just such that you want your v in meters per second, this is going to it's going to end up giving you a force in newtons as long as you've got this formula that you're using. Okay, so here he's got a race car, 1,000-kilogram race car, crossing the finish line. So it hits the finish line, and it's traveling 175 miles per hour. And after crossing the finish line, the race car is shifted into neutral. So only the force slowing the car down is the air resistance. If the air resistance is this, where v is the speed measured in meters per second, f measured in newtons, how much time would it take for the car to slow down to 60 miles per hour? So the idea that it crosses the finish line here, 175 miles per hour. You can do a little conversion here. We get it in meters per second. It's going to slow down to 60 miles per hour, and that's that in meters per second, so our units work out nicely. And we're going to kind of do the same basic notion of this. We're still playing with F equals ma. This is a little simpler, that we just have this resistive force. I did put in a minus sign. It's got to be back in this direction. We'd run into trouble if we had it this way. It would actually be speeding up, and it would be going faster and faster. But we've got a resistive drag. It's moving this way. It's going to be opposite that. So there should be a minus there. We've got the mass of the car, and acceleration is dv dt. So what we want to do is something very similar to what I did in the previous one, is this idea of separation of variables. We get our v on one side, our t on the other side. So I take this, I leave the 0.61 there and a minus. I'll take the 1,000 down. Big thing is I take the dt over to this side. And on this side I have dv, and I'll divide by the v squared. So I separate variables. V on this side, t on that side. Now the thing that I need to do is integrate this. This is a bunch of fine steps here, little dt's and little dv's and little dr's. We're going to be integrating this thing as we go from 175 down to 60 miles per hour. So when we integrate this, we need to watch our limits. We're going to have the t is going to go from just to 0 to sometime t. I'm going to want to solve for that. I don't know what that time is, but I'll put it in there as a limit. And then on this side, I want to integrate, this is integrating with respect to velocity. So that would be the initial velocity and the final velocity. The initial velocity isn't 0, remember, it's 175, or 78.2 is the initial velocity. The final velocity isn't 0, it's 26.8. So we've got actual numbers there. Doing the calculus, this is a v to the minus 2. This becomes a minus, when we integrate it, minus 1 over v, evaluated at the limits of v initial to v final. And so I end up with an expression like this. This dt just becomes all of this constant times t. This was a minus. Oh, I got carried away with minus signs. I have a minus sign over here. I knocked those out. And then I have a v final all over v initial when I do this with these two limits. Hopefully you can see that. Then it's a matter of just kind of sticking in these numbers. I use the SI terms here along with this, and then I can plug in and I get that time. So the math is quite a bit simpler than on the previous example, because we had the two forces in there and it got messier. We had to use you have to change the limits and all of that in order to solve. So the calculus was worse, but the basic process is the same. Again, we use Newton's laws. We get a differential equation. We want to separate variables. Check out how this works out. And that would be the time it would take to slow down to 60.
So what I don't get about this one is that on the previous page we had that formula that relates velocity as a function of time. Not that.
Yeah.
And it seems like you could get time from this too.
Oh, yeah. Okay, from this, yeah, this could have been a question, like this is falling. It was based on starting at 0, but you could say, how long does it take for this thing to get up to 60 miles per hour?
You use that same formula to solve that.
No, this particular formula is for the special case where resistive force is proportional to velocity.
Isn't air resistance proportional to velocity?
Usually at lower speeds, at higher speeds, it tends to be proportional to the square.
So it's exponential. So it's
for faster moving objects.
Yeah, for faster moving objects. Consider in any problem that he gives you, he needs to specify which of these you're going to use. Okay. So if it's not clear to you, you want to go up and ask him if you want to make some assumptions. Because offhand, again, resistive forces, they're actually all more complicated than this, but this is a reasonable approximation. Yeah, there's another question. Yeah.
I have two questions. So would you recommend memorizing the formula, or knowing how to derive it?
Okay, I would recommend, I don't think he's going to ask you to derive it. In fact, the book kind of glossed it over. They more or less said, here's the solution, put it back in, and you'll see that it works. And that's ultimately all you need to do. If he asks you anything related to this, it would be, you could just pull out this equation. So I would say, probably for the exam, it wouldn't be a bad idea to just store it up here, and then next week forget it. You know, this problem is different in that it's velocity squared, and so it's a different force, and therefore that other equation does not work for it. Here we, in a sense, are deriving the equation for it and getting the solution for that equation. Yeah.
How would the equation change if it was moving, or if it was moving in circular motion? Like, you know the part when you say, when you put in the dv over dt, does that change to? Does that change to v squared over?
You're asking a good question. Oh, I see. Yeah, the acceleration would be a v squared over r. So I think we'd need to start to turn that.
So it wouldn't be a differential equation?
It would be a differential equation. It would be a different differential equation. And one thing he's not interested in doing, this is a physics class, and while this is a little bit of an exposure to differential equations, it would only be one of these two that he would maybe focus on. And as I've been saying, this one is one he's been using a lot. He'll because the math is simpler, he can see, do you have the ideas without getting caught up in U substitutions and strange integration. So it would be good to see how this works, and he would expect, if asking this kind of question, to see your work, or you're likely not to get full credit. Okay? Okay, again, I don't want to push this too much other than this is a good problem to definitely look at. Okay, let's get into energy. Energy has some real powerful techniques of solving problems that can be a lot simpler than the forces. We took quite a bit of time with forces. Generally, they're harder to deal with. Forces have magnitude and direction. Nice thing about energy is that we can turn everything into simple scalars. And I'll show you how that we can make some what would be really difficult problems to using Newton's method, we can make them really simple. And so we like that. Let me just start off with to show that ideas of energy really come out of Newton's laws and ideas. And this idea of energy never occurred to Newton. So this was something that didn't occur to him at all. In fact, the whole idea of conservation of energy didn't really take off till we really understood heat better. And we, usually we deal with something, something sliding along, dragging on the ground, and we say, well, where did the energy go? Well, it went to heat. Well, we're going to have to understand heat better, and you'll do that in Physics 123, but for right now, it's just sort of lost to the system. Anyway, we can go ahead and derive the work energy idea. And I thought just start off with something simple. Suppose we have a frictionless tabletop here. We've got some block here, some mass with it. And we've got some force I could be pulling on this thing. And it could be, cause that force would have a component. Again, frictionless, just keep it simple. It's got a force in the x direction. That's going to cause this thing to start to accelerate. It's going to pick up speed. So maybe had some initial speed, could have that, and then as we do this work, it's going to end up with a greater final speed after we move through some distance. So applying this force through this distance is something we'll call the work, but let's come to that in a moment. But the idea that this should just cause an acceleration, that acceleration should lead to a larger velocity. So keep in mind that the forces F times the cosine of theta is just going to be equal to the mass times the acceleration in the x direction. Simple. What about these other things, the normal force and mg? What are they doing for us? Nothing in terms of the motion. There's no force in the direction of motion. They're at right angles to it. So they are not doing anything to increase the speed of this thing. okay, so it's only this particular component that's going to lead to the acceleration. Okay, now think back to your kinematics. We just finished that unit, and this one is an equation we didn't use too much, but it was part of constant acceleration, and we should have that here, constant acceleration. That should be v final squared is equal to v initial squared plus 2a in the x times delta x. Do you recall this one? It came from the first two equations that we got for constant acceleration by eliminating the time between them. In fact, that's an important clue. Energy will not tell us about the time when things happen. So there's a limited information we can get from it directly. Sometimes we can do it indirectly. But let's start here first with the kinematics of this. And let me just take this kinematic equation and multiply through by 1/2 m, and this side, the 1/2, the 2 cancels with the 1/2, and we just have m times ax. Oh, mass times the acceleration in the x, that should have been this force on it, F cosine theta, times delta x. And these two terms, 1/2 mv squared, what do we call these? That's the kinetic energy. So we give it a name because it's important. But it's, wow, kind of a strange looking thing here, 1/2 mv squared, minus 1/2 mv squared. This is the change in the kinetic energy, and that should be equal to the force in that x direction times delta x. And this is what we're calling the work done. So the work done by that force as it's causing this thing to accelerate and pick up speed, leading to a change in kinetic energy, is the work done by that force. So this is strictly a constant force in the x direction, but what can happen here is we can generalize it more. Let's say this gets to be powerful. Let's say we just take some path through space. And as we go through that path through space, we could be subject to a number of different forces along the way. Kind of focused on just one little point here where it's going to move. And the idea, this force that's acting on this happens to be here. And I just have one with a tangential component as well as a perpendicular component, just resolving this F net into two components. One is tangential, causing a tangential acceleration. You can think of the motion of this thing as actually traveling along a curved path with instantly it's traveling through, this is a circular motion in a sense, and that we've got a force that's in the centripetal direction. That is just causing us to change direction as we go through space here. The thing that's causing us to speed up or slow down is this tangential component to the force. So the idea is, well, if I just do this on a small little scale, delta r, even if the force isn't constant, for a little tiny dr, we can say that there's going to be a little bit of work done. It'll be the force, or the net force that we have here, times the cosine of the angle that that force makes with our path, or we say our displacement. Our displacement as we go through here will be a little delta r. And that should be equal to a small little change in kinetic energy as we go through here. Okay, so now the idea is we've got, this becomes a small differential amount of work, that's delta, and then F net. We've got a delta R will become a dr. And we can use a formalism with math. That is that dot product. You've maybe seen it before in math. We were introduced to it here, that if we just in general, our dot product represents A dotted with B, should be, these are vectors, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So I can write that, instead of that cosine, I can write this as an F dot dr, so just kind of our formalism with that. And that's going to equal to our change in kinetic energy. Now, the idea is this is the work done just for a small little change, and leading to a small little change in kinetic energy. But the idea, we could take it through an entire path through space, so this could be rather complicated, where the complicated forces, but in principle, we would just say the net work is, we're just going to add up all our works as we go through this path, and then we're going to integrate F dotted with dr, and that should be the summation of all our little delta k's, or dk's. And the net work should be equal to the net force dotted with dr. Okay, so that's kind of what we'll call the net work in the most general sense, the integral of that. And that's going to be equal to K final minus K initial. All our delta K's are going to be whatever we started with, K initial, we ended up with K final. So it's kind of waving my arms, but this, hopefully you get a little bit of a sense of that this is actually something very powerful from something that would be really difficult if we had some really strange forces. Now, the idea that the net work is due to the net force dotted with dr, so this is the work of the entire force. But now this net force, we can also say, well, that could be broken up into a bunch of components, like, and we would call these the sum of all these components. And so the net work is the same as the integral of the sum of these components. The sum of the components of the force is the net force, and then we're going to integrate that. Integration and summation, they're both summation processes. When we add things, we can add them in any order. So you've maybe seen this, or if you haven't, you'll see this in calculus, where you can flip the order of these and do the summation first and then integrate. So the idea, if you've got a number of other forces that are acting, you can get the work of an individual force, not just the net force, but all these individual works, and we would just do that to sum up the individual works on these things. So the net work done is the same as the sum of all the works done by the separate forces. Now, this is complicated and it has a lot of big implications. We're going to primarily look at some fairly simple forces. Gravity, we'll deal with the work done by gravity. We maybe have a spring, an elastic force, a work done by the spring. We can have friction, that'll be work done by the friction. We also can have work done by maybe some other external force. And the idea that the net work, or the sum of all those works, have to equal the change in kinetic energy of this thing that we're applying these forces and works to. Okay, so let's look at these individually a bit. Work done by gravity. Let's say we just have a block here. I'm just going to drop it. Great. Started out at 0 velocity. It's going to fall. It's going to pick up speed. And we know how to do this kind of problem. I'm just focusing on the work here. The force is down, mg. What we want to do is dot that with the displacement. That is displacement. It's going from here down to here. So I'm calling that h is that displacement. And dotted with g. Now, the displacement it's coming in the negative sense. It's coming this direction. It's in the same direction as the force. And so when they're in the same direction, it's causing this thing to speed up. So gravity is doing work. The work that gravity is doing, when we look at this, cosine of 0 degrees, because h, the displacement and the force are in the same direction, that's 0. And the work done by gravity as it falls is mgh. Okay, so chose that h for a reason, and hopefully this looks a little familiar by now. What is that? Looking like potential energy, but now let's be careful. What about the change in potential energy? We want to define this, and the idea that change in the potential energy of gravity, we're going to define, that's what these three represent, is equal to minus the work done by gravity. You say, well, whoa, how do you know this? Well, we're just playing a game, and what we're doing is actually just a real clever mathematical trick here, and I'll show you where this trick comes in, is that we're going to define the change in potential as minus the work done by gravity. Now let's look at the change in potential energy. You've already been dealing with it. If this is zero potential energy, what's the potential energy up here? No. MGH we'd say would be the potential energy of this thing. As it falls, it's going to go down, and so it's going to go final, which would be 0, minus initial would be a negative MGH. So the work done by gravity is positive, but the change in the potential energy is the negative of that. Okay, this is a subtle issue, but the change in any potential energy is equal to the minus of the work done by that, whether it's gravity or any kind of force. This is kind of our definition, and I'll show you the cleverness of why we want to use that negative. But the idea, again, is the change in the potential energy. It ends up at 0. Initially, it was MGH, so it's a minus MGH. And that was the initial gravitational potential energy up here. Okay, so kind of playing with the ideas of what you've already seen, and also so you can appreciate where we're going to be going with this. So that's work done by gravity. Just a quick one. If I happen to have an object and I throw it up and it's going in this direction, where gravity, the force of gravity is down but the displacement is up, then instead of being the cosine of 0 degrees, it might be the cosine of 180. So as it's going up, gravity is doing positive work, and it's slowing it, is doing negative work. It's slowing the object down. Okay, let's, it takes a little bit kind of getting used to this. Now, gravity is also what we call a conservative force. So I could start with that block and just drop it a distance h and see what happens. Or let's say I put it on some kind of mathematical slide here where this is frictionless. And this thing is going to start to go down, and this is just one point along the way where, of course, gravity is pointing straight down, but the displacement's off at a slight angle. And that angle is making angle theta with respect to mg. So the idea, what is the work done by gravity here? Well, it's mg is the force times the displacement dr times the cosine of the angle theta. And now what we can look at here, if we turn things around a little bit, that dr, and just take dr times the cosine of theta, this is going to be equal to a minus dy. It's coming down, and so dr times the cosine of that would be dy. I should have put a minus here since it's obviously headed down. That minus dy is dr. And so the work done by gravity is just mg dy. And so when we do the integration by adding these things up, I'm integrating with respect to y, and the work done by gravity, by this complex path, is still mgh. And there's still the change in potential energy from up here down to here. Seeing this, how this works, that it works regardless whether we just drop this thing or send it down on this slide, we get the same change in the potential energy and that same change in the kinetic energy. So what's kind of strange is if I just drop this thing, the velocity that it would have just as it's about to strike the ground here would be the same as it is if it went on this slide, regardless of the shape, as long as it's frictionless. It's going to end up down here with the same speed, moving in this direction. So they're not necessarily moving in the same direction, but the change in potential energy from here down to the ground is the same, regardless of our path. That the time won't be. This could take a lot longer, and from energy principles, we can't say about the time. Okay? So that's something that's limited. This can also be a good clue as to, do I use force methods or should I use energy methods? Energy methods are generally the simplest, but sometimes you're kind of forced to use force methods. Sometimes we can marry the two, which we'll look at in a moment here. Okay, so that's kind of gravity. Hopefully you kind of have a pretty good grasp of that now. Also, a spring is another what we call conservative. The idea is I can stretch out the spring. I have to do work to pull it aside. I have to pull it aside, and then I get it here. I can release it, and then the spring can do some work for me, and it will start to set this thing into motion. And the idea that it can store energy is this idea of a conservative force. Okay, now the force of a spring, we stretch this thing. First of all, we have the equilibrium position, where if it's no force on the spring here, it's relaxed. We have this force here. This is going to be 0 here. We're going to measure our x, the stretch, this way, either a plus or compress it with a minus. The force of the spring is a minus kx in the negative direction. If x is positive, it's negative, so that just pulls back in this direction. If we take this and we compress the spring, the force of the spring pushes back. But nicely, this equation will still hold. The x would be negative, and then negative times a negative would make it positive. So when I compress this thing, it gives me a force in the positive sense. Okay, so once I know this relationship with the force of the spring, let's get the force of the spring. Let's say I've got to, let's say, cock this thing. Typically, I would have to give some of my energy to take and pull this thing back. And then I'm going to release it and let the spring do some work. And it would start off at, it would be F dot dx. That's going to be the displacement times the force. And we're going to go from some x out to 0. This will be in the negative direction. The spring is, force is back this way, dx is negative. And so the work the spring did from these limits is going to be, it's easy to get messed up with signs, so you want to work through these, but is going to be 1/2 kx squared. That's the work that the spring did. The change in the potential energy of the spring is minus the work the spring did. But consider that when it was stretched out here, it had its big kinetic energy. When released, it went through here where it went to 0. So the change in the potential energy are 0 minus the original potential energy. And we can summarize this well with just saying the potential energy of the spring is going to be 1/2 kx squared. So wherever it's at, whatever that x is, we'll use the potential energy for that. So I'm going to have maximum potential energy when this is stretched at the maximum amount. I release that, and it goes through the origin, and where the potential energy would be 0, where x would be 0. So this kind of summarizes this. So again, let's look at the idea of a spring, and we're going to tie these things together here in a moment. One other thing, we've got friction. Friction is a non-conservative force. For us, it just takes away from us every step of the way. If this thing is moving, let's say a block moving with some displacement this way, friction always wants to fight it. It's going back in the other direction. So the work friction does is F dot dr. This is going to be F times dr, but they're going to be 180 degrees to one another, which is a minus here. So the work friction did is minus the frictional force times the distance that this thing moves. And friction always does negative work. You want to consider that work is something, if it's positive, if you're putting energy into it, if you're taking that energy out, you're doing negative work, you're taking energy away from it. And this is what friction does. It takes it away from the object. What happens to it, ultimately, we're going to say, well, it gets stored in the form of heat. And the idea that heat would be equal to whatever minus the work friction did time. That would be just the friction times the distance. So this is going to be a positive quantity. You consider the work friction did is negative. It's taking it out. Where does it go? It goes into heat. Now we can look at this as almost a store of energy, a bit like a spring storing energy. It is thermodynamic energy. For us right now, we're not going to be able to get any of this back out. In Physics 123, you'll look at some ways of getting that energy out of that heat. But again, more on that later. So again, friction always does negative work. Okay, now let's put these things together. Okay, the net work is equal to the change in, the sum of all the works done by all the individual forces is equal to your change in kinetic energy. We've got the work done by gravity, the work done by the spring. Let's say the work done by friction, let's stick with those for right now, is equal to your change in kinetic energy. Okay, now here's where the sign comes in rather nicely. We say the work done by gravity is equal to minus the change in the potential energy. We're coming up with a new idea, this idea of potential energy, and we defined it that way, kind of a mathematical trick. The work done by the spring is minus the change in the potential energy of the spring. The work done by friction is always negative. It never does positive work, never puts energy back into the system. It always takes it out. And what we're left with is a change in kinetic energy. So the idea of the change in gravitational potential energy would be U sub g final minus U sub g initial. And we have this minus sign. The spring is going to be a minus here, and then we're going to have inside here the change in potential energy of the spring is U sub of the spring final minus that initial. Again, this is always holds, and kinetic energy would always be final minus initial. Okay, now let's separate terms. Let's move all the initial terms over to one side, the final to the other. So I've got my initial terms, I've got a minus times a minus, this becomes a plus. And this becomes a minus, and a minus, this becomes a plus. I've got a kinetic energy initial, it's a minus here, I take it over to the other side as positive. On this side, I've got, I take minus U sub g final, I'll take it over to the other side as a positive. I've got U sub s final, I'll take that over to the s, over to the other side as a positive. We'll take the kinetic energy final, well that's already on this side. And then let's take this minus the friction, the work that it did, over to the other side. So that minus sign becomes now positive. And this is going to end up being what we'll call our heat term. But now the way we've arranged that, and it all came into play with these clever use of these negative defining things, we've got everything, we've got all the initial terms on one side, all the final terms on the other side, and they're going to be equal. So this is the idea of conservation of energy. I can take my various forms of potential energy. I can add the gravitational potential energy, the elastic potential energy, and the kinetic energy, that energy initial, and equaling, can play the same game on the other side in the final. But on this final side, we'll put the heat. The book doesn't do it this way, that leaves it on this side with a negative force times distance. Dr. Young and myself like to move it over here so that we have the idea of conservation of energy for all the forms of energy we're dealing with here, thermodynamic as well as elastic and gravitational. Let's take it. Once we have this, it's very powerful. Now, as far as doing problems, all of these are scalars, so there's no worrying about components. One thing, kinetic energies, are they ever negative? Would it be possible? So when I have mv squared, if v is plus or minus, when we square it, it's got to be positive. Kinetic energies are always positive. The elastic potential energy of a spring is always positive. Whether if you stretch it, you've got a certain amount of potential energy, or if you compress it, you've got a certain amount of potential energy, and that will always be a positive quantity. It's 1/2 kx squared. X could be either plus or minus. When you square it, it's positive. Now, the only thing that you maybe need to worry about signs is gravitational potential energy. It's either going to be plus or a minus. The idea will be that you put your zeros at some point on the diagram, and if you're above that, you've got positive potential energy of gravity. If you're below that, you've got negative potential energy of gravity. And so this, as we do problems, this can greatly simplify things, that as far as knowing what to use and what signs to have, things can move very quickly in doing problems. Okay, so let's look at a couple here. One is the idea of this pendulum. It starts at 20 degrees, 0, and is given an initial speed of 5 meters per second. So it's actually maybe pushed and it's going to swing, and it's going to swing up to some height. He gives you, if the length of the pendulum is 3.25 meters, what is the maximum angle that the pendulum achieves as it swings to the other side. So it wants to find what is this angle up here. I think we could use a better picture here, but this is a little better, but not much better. We do have some geometry here. We want to get the initial energy at this point. So we'll say the initial energy is all the forms of energy. We don't have any springs in here, so we've got kinetic energy. The potential energy would be just that of gravity. So we have some kinetic energy, 1/2 m, and the 5 meters per second is the velocity. Wow, I don't know m, but it might just drop out. Gravity should be mgh. That's m and that's g. The h, though, is the height that it's above 0. So I'm making the very bottom here to be 0 gravitational potential energy. It's sitting above that, so mgh. I need to find that h1. This is a common one that you need to get. What the basic idea is, to get this distance, I take this whole length here. This is the length L of the pendulum. Picture didn't look real good. They should swing down. This should be a circular path here. And so this should be L between here and here. And if I can take this distance, which is going to be L times the cosine of 20 degrees, I get that, and I subtract it from L, that leaves me with H1 there. So I have L minus L cosine 20. You want to make sure you know how to do this kind of trick. And it gives us the length of the pendulum and 20 degrees. And so I calculate what H is. That would be the first height. And that allows me to finish off the potential energy. I have an M there. I still think it's going to drop out. But this would be the initial energy with everything except M in there. Then we look at it on the other side. It's going to swing back over here to some maximum height. And that's where it would just stop. And so the final energy, it would be the kinetic energy of that would go to 0. The potential energy is going to be mg, and it's going to be the height above this, h2. And I can use the same basic trick here that h2 is going to be L, this whole length, minus this length. This is L times the cosine of theta is that. And so again, I'm using the same relationship, and we end up with 1 minus the cosine theta. I don't know what that is yet. But with my energy, kinetic is 0, but the gravitational potential energy is going to be mg, and then this is actually the h2, the height of this thing. So you have to do some work getting at that. Then the idea of conservation of energy, and E initial is equal to E final. I can take this equal to E final. Both of them had that M on both sides, so that ends up just canceling. I don't need to know the mass of that pendulum. And then you can follow this and go, and I can get that angle, 56.8 degrees. So it's probably a good one you kind of work on your own. Do get this kind of trick of how we get these H's here. That sometimes gets employed in other types of problems, so you want to make sure you're ready for it. Okay, how about, here's another one. This kind of wraps it all in. We're going to have a 10 kilogram block that's going to slide down. It's going to go across 5 meters of rough road where there's friction. No friction down to here. Friction, then no friction. It's going to then go up an incline. It's going to collide with a spring and is going to compress the spring some distance x. It'll come momentarily to rest, and then it would probably start to rebound, come back. So this is a 10 kilogram block. It's released from a point 4 meters above the floor. The track is frictionless except for this 5 meter length in the middle, which has a coefficient of friction 0.2. As the block slides up the 10-degree incline, it runs into the spring constant, or spring with a spring constant of 2,000 Newton meters. To what length is the spring compressed before the block comes to rest? So what he's asking for, what is x? And it comes to rest. The on-stretch spring is 1 meter from the base of the incline. So when it's relaxed here, this is 1 meter. So got a lot going on here. Now, the idea of energy being conserved throughout the whole motion, we could say, oh, I've got potential energy here, no kinetic energy, comes down here, it picks up some kinetic energy, goes across here, it's going to slow down, it's going to lose some kinetic energy, then it's going to go and start to build potential energy as it goes up. It should be slowing down that way. Then it starts to compress the spring, it's going to slow down. Seems like it could be a really long, laborious process. But energy is conserved throughout the whole motion. The energy here is the same here, 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 here. Any point along this thing has got the same energy. So as long as strictly asking for, how much this spring gets compressed, we can take a look at what is the energy initial, and then go right to where it's final and set the two equal, since they should be the same. So let's look at that. The initial energy right up here is up there, the kinetic 0. There's going to be some gravitational potential energy. I believe I made this just 0 at the bottom. And so it's mgh, and the h is 4 meters. So that's easy. In fact, we come up with a definite number there, 392 joules. There's no elastic force, so no elastic potential energy. Then we can go to the final energy. Now here we need to be careful. There could be some kinetic energy, and I like listing out the forms of energy. Potential energy with gravity, potential energy of the spring, and also heat energy. That's what friction does. And let's kind of fill these things in. The kinetic energy is 0 because it's going to come to rest. The gravitational potential energy is mg, and the h that is above this platform is going to be 1, it's already 1 meter up here, 1 plus x times the sine of 10 degrees would be the height of this thing. So this is the gravitational potential energy. Then we need the elastic potential energy. That's 1/2 kx squared. 1/2 of this is our k, and then we have our x. And then we also have, this last term is heat, which is going to be friction. I didn't draw separate free body diagrams. It's pretty obvious on a flat surface, the mg times, that's going to be the normal force, times that 0.2 is going to be the force of friction, times the distance that it moves. It moves across here 5 meters. I'm just accounting for the heat that's generated in this little path here as I moved across here, since everything else is frictionless, so no heat generated there. So these are such that I can stick in the numbers, and E final also should be equal to E initial. E initial was 392, so I can go ahead and set that equal to E final. And the rest of these, when we stick in the numbers to simplify this, we end up with an x. Ooh, it's looking like a quadratic though. Kind of put that into standard form, and you know how to do this, and you can do the quadratic and end up with an answer. Sometimes, you know, the math with the quadratic, you're going to get two solutions. There's going to be another point that's negative. It's going to be sitting down. What's happening, sometimes the math gets in the way of the physics. What's going to happen is the block is going to compress this thing to this point. This is the first place it's going to stop. And then the idea is, well, now as far as mathematically, the math thinks it's stuck to the spring. And so it's going to start going back down, and it's going to go back down in the negative sense, but it would stop here somewhere along the way. And it would stop when x is in negative, that is when it's down here, 0.5. So anyway, you can give some thought to that. Sometimes it's a little difficult to figure out which solution we want to use for our quadratic, one that's physically significant, and I believe it's going to be this one. Okay, so again, this one, it really helps to be able to just say, hey, I have the energy here, I want to find it here, and go right for it from there to there, and we kind of, all this other stuff like friction gets tied in there, and we don't need to make a special case about every point along the way. Okay, okay, here's another one. Okay, 1 kilogram mass is hooked to a massless spring with a 500 Newton meter spring constant. A light string is attached to the mass, looped over the massless frictionless pulley, and attached to a 3 kilogram mass as shown. So we've got that. We've got a 1 kilogram mass. It's connected to this spring. And okay, now he says, this is a little hard here. If the masses are released from rest and the spring unstretched, how far does the spring stretch? Okay, so let me try to describe this. The idea that we're going to, let's say, place this thing, and we're going to maybe hold it here while we have the spring. The spring is relaxed. Otherwise, if we weren't holding this block, it would tend to compress the spring. So we're going to hold it there with no stretch in the spring. It's relaxed. We're going to take this cord and connect it over to here. And imagine we're going to kind of hold both of these. And then we're going to release them at the same time. And this one's going to go down, falling, and that's going to pull this one up, and that's going to go up. Okay, so we've got, this is a case of a coupled system. We've got two of these. In a sense, this guy's going to fall. Its gravitational potential energy is going down. It's going to drag this one not only up where the gravitational potential energy is up, but as it moves up, it's also going to stretch this spring a little bit. And the question is, what is the question? If the masses are released from rest and the spring unstretched, how far does the spring stretch? So basically, how far does this thing go up? However far this thing goes up, some distance x, it's going to stretch that spring. So I've got here a little bit sketched, I don't know whether it's any better, but this is that surface. Now here's a trick when we do gravitational potential energy. Ultimately, when I was showing you where this stuff came from, it's ultimately all due to the most important thing is the change in gravitational potential energy. This guy's dropping, this guy's going up, or let me do it this way, going up. Now, what you can do in doing these problems, you can say that since I only really care about what's going to be the change in potential energy here and the change in potential energy here, I can start it really wherever I want. And it's okay to say for this one, I'm going to use the gravitational potential energy 0 here. And for this one, I'm going to set this one 0. And then I'll look at how they change, how this one goes down and this one comes up. So this seems a little shady at first. It takes a little getting used to, and I can make a tighter argument, but I think we've still got some stuff to do here. So hopefully this is okay with you. Now, the idea of the energy, we've got, as this thing falls, it's giving some of its energy over to this. It's going to lift it and stretch the spring. So the idea, we've got two things in motion. When we do the energy, we're talking about the whole system and the energy. And I'm kind of regretting here I don't have some more terms. We've got kinetic energy terms. Actually, there should be two of them. There's this one's kinetic energy and also this one's kinetic energy. Now, they should probably have the same kinetic energy as they move because this cord is stretched and is going to be moving as these things are moving. They would tend to just sit and oscillate. He's asking for just getting down to here and before it snaps back, but it's going to be doing this kind of thing. So we've got two kinetic energies. We also have two potential energies, gravitational, because we've got two masses. And we only have one spring, so we just have one of those. So when I do this, I'll do the initial. And what we're doing, since I'm starting this thing, I'm holding these things, and everything's relaxed. The spring is relaxed. These guys are relaxed. I'm going to then release it. My initial energy is these two are not moving, so the kinetic energy is 0 for both of them. And then the gravitational potential energy, I'm going to make it 0 for both of them. That is where they start. And then the spring is 0 because it's not stretched yet. So after we release it, this thing bottoms out before it snaps back. The final energy is, again, momentarily these come to rest before this thing jumps up. So the kinetic energy is really back to 0 when it gets down here, if you think about that. The potential energy, gravitational potential energy, is going to be two of them. There's M1, that first one is going to be mg times x times the sine of 30 degrees. So x times the sine of 30 would tell me how much this thing went up. And then this one is going to go down. If this is 0 and it goes down here, that would be a negative, a drop in potential energy to this position x. And then the spring will have stretched an x, so that's going to be 1/2 kx squared. So then it's a matter of just setting E initial equal to E final. We made E initial 0 just for our clever use of that. Again, we have these terms coming out. We've got an x term for along the slope. This is for this one dropping a distance x, and then this is the spring as it's getting stretched a distance x. So big thing is we need to solve for x. Luckily, it first looked like it was going for a quadratic, but we get an x and x squared that cancels out. It looks like it's just a simple x is 9.8 centimeters would be how far this one would go down. Okay, so take a look at this one. Hopefully, my simple argument, I can give you a better one if you want to see it, that I make these two gravitational potential energies the same. And you can just specify where it starts out at the initial and call that 0, or at the final, call that 0, just so you're doing it at the same setup for the problem. Hopefully that makes some sense. It greatly simplifies the problem. Okay, one more. We talked about some pulleys. Here's another example. Okay, we're free. Okay, I guess it's 4 o'clock, but we're almost there, so hang in there. Blast through. Okay, we have an object of mass 1.5 kilograms on the table with a coefficient of kinetic friction 0.3. It's connected to an object of 0.25 kilograms on this side. So this is the 1.5 kilogram on the table. The other mass is 2.5, and through a very light movable pulley. Oh yeah, now this cord here is attached to this one. It comes over here. Now my picture's looking a little bit, I mean this to be when this is here, this guy is, let's say, here. And then what's going to happen is this thing goes down, is going to pull this pulley. It's also going to pull this thing this way. Hopefully you can kind of see that. So this pulley is being pulled over here along with, and this is just connected to this pulley. This string is tied over here on the wall. It comes around and then comes back to this mass. So the idea is when this thing pulls forward like this, it's going to pull this thing a certain distance. Now, here's where you want to look. That when this goes down, x2, to some distance, it is directly connected to this, and this pulley is going to get pulled a distance x2. This is probably a kind of a better picture of the basic idea. I've got this pulley is going to be represented at some initial point, and then it's going to be pulled over to some final point, and that's going to affect the position of this mass. So again, as this comes down some x2, this pulley is going to get pulled over in x2. And now the idea that we've got a certain amount of line up here and a line here, because this line comes around here, back to here, that if I take up that amount of line here and here, 2x sub 2, that should equal the amount this has to move over, because we're in a sense shortening this string by this amount, 2 times x2, and that's going to move x1 over. This is where I'm saying things can be tricky. So I'm saying that x1, the amount this moves, is going to be twice what this one moves. If you can see that in terms of a displacement, and I admit these can be very tricky to kind of see what's happening. Hopefully you can kind of see what I'm saying. I'm having trouble even expressing this. That x1 will be equal to 2 times x2. Now once we get that basic idea of the displacement, then I can go ahead and take the derivative with respect to time. So the velocity of one should be equal to 2 times the velocity of the other one. So that's going to be important. Okay, so now we've got this set up here. We're going to release that. And this mass is going to start from rest, and it's going to fall 10 centimeters here. And then using conservation of energy, what is the speed of the 1.5 kilogram mass? So they're really asking for, what is V1? What is V1? Okay, so from energy, after we get that part out of the way, we can say the initial energy, we've got kinetic energy. This is a system. We've got two of them, K1 and K2. They're both starting from rest, so that goes to 0. The gravitational potential energy of the first one, well, ultimately we just care about the change in potential energy. It's not going to really change. So I'll just say, hey, let's make that 0 to begin with and 0 to end with. And then the potential energy of this other mass is going to be up here. We could call that, it would be that gravitational potential energy. And that's going to be equal to mg times x2. That is going to be mgh. So down at the bottom, I'll make my 0, and I want to get the height of that. So that's mg times x2, the h. And so this would be the initial energy, is strictly just that potential energy. All these other terms go to 0. And then the final energy, they're both going to be in motion. We're going to have a kinetic energy of one, kinetic energy of the other. We've got the potential energy of the first one, gravitational, which we say, hey, it's on the tabletop, it's not changing. I'll just make both of those 0. And then the gravitational potential energy of the second one, that is going down, and I expect it to drop. And then So that's, and we had, oh yeah, we have friction too, duh, yeah. Friction along this surface, and so that would be this friction term times the distance that it moved. Friction here is going to be that frictional force times x1, that distance. And we're going to put that in. So we want to add these up, the kinetic energies. We ultimately want to get V1 is what he wants, the speed of that one. So the kinetic energy of that block here is just 1/2 mv squared plus the kinetic energy of this block as it falls, 1, and this is 2.5. Now the velocity there should be V2 squared, but I can replace V2 with a divide through 1/2 V1, since that's what I'm going to be looking for. Put that in. Zero potential energy. I've got this potential energy that it falls. I've got everything here. When I set those initial equal to final, I can solve for V initial and I get a 1.21 meters per second squared. Okay, so this is kind of an example. One, it's a system, so we have to deal with all the parts of the system. As this one drops, it picks up kinetic energy, but it also pulls this and does work getting this thing to move. And then these trickiness with these pulleys. Again, these systems can be a little tricky. Yeah?
If the problem is asking for acceleration,
Oh.
acceleration of M1 would also be double that of M2.
Correct.
Okay.
Correct.
And could you get acceleration from taking the derivative of that V squared second to the very bottom line?
Oh, no. We're only going to, this only yields one answer. If we're going to take any kind of derivative, we need to have a continuous function. So in a sense, we've already kind of solved the problem. Now, you might say, hey, well, question could have been, well, what is the acceleration? That would be an important one. Now, one thing the energy methods do not simply give you the time that it takes, okay? And they don't generally express what the acceleration is. Now, this type of problem, though, will be a constant acceleration problem. So you can sometimes answer some of those questions like time and acceleration that aren't normally part of energy. But if it is constant, you can use the kinematics, and that can in turn tell you what it is. But that would only be good if it's a constant acceleration. In general, if it's not, it's going to be messier than that, and you're going to have to do it the hard way. Okay? Whew, okay.
What happened to one of the V1s? You have two V1s squared right there. What happened to those? On the second line, we only have one.
Oh, in this line? I think what I did is I combined these. I had a V1 squared and another V1 squared, and so I added these.
Yeah, it doesn't come out to that.
Ooh. Okay, it should. So this could be another one. I better check the numbers.
Yeah. So we have 1.5 times a half, right? Plus another 2.5 plus a half, right?
Yeah, or 2.5. And then we have this is going to be squared, so there's going to be a 4. 4 would divide 3 by 4.
Okay.
So okay. Okay, look at this with suspicion. Go back and see where I screwed up. Okay, yeah. Watch everything I do with suspicion. Okay. Let's see. What do we got here? Oh, okay. We're almost there. I think this is a good one to look at. Here's where we can combine energy methods with force methods. We have a bead that slides down a straight wire with a constant frictional force of 0.35 newtons. It then so it's sliding down a straight loop. It's going to go around this loop. So this is a bent wire. It's been my experience. Some people totally don't get the picture. This bead is like a little necklace bead that has a hole cut in it, and it's riding down a wire. That wire does a loop-to-loop as it comes around, and the bead is going to go around. The bead is riding on the wire. If you're looking down the barrel of the hole of the bead, it's going to look something like this, but I'll come back to this in a moment. Energy methods. Part 1, we'll look at this, and really what I'm after here to do this, first of all, what is he asking? Slides down a wire with a constant frictional force. Now, he tells us what this frictional force is. Little thing is, he's trying to save you a little bit of work. He didn't talk about the coefficient of kinetic friction. He's just telling you that there's a constant frictional force of this amount coming down. So mu's whatever it's got to be to make that happen. Then the bead slides along a frictionless wire. So this part of the loop is frictionless, which is good, or it really would get messy. The radius of the circle is 10 centimeters, and the bead is released 50 centimeters up from above the ground. What is the magnitude and direction of the normal force on the bead at the top of the circle? Now, this idea, we need a normal force. We need a force, and generally this is not part of energy. We need to do some stuff with forces, but let's look first at this energy stuff. From this, we should be able to get the speed of the thing up on top. So part 1, we'll just look at the initial energy. The bead is up here. The kinetic energy is 0. There's just gravitational potential energy, mg and h. And there's some potential energy up here. Okay, and then, so that's energy initial here, and then I've got energy up at the top. This is up at the top of the loop. Now, what I'm doing again, I'm just going from this point to this point. Energy is conserved along the way, but I can get my answer very directly. My initial energy, my energy up on top here, has some kinetic energy. It's going to have some gravitational potential energy. That is, if I make the ground 0, it's up there in the air. Also, as it comes along here, it's going to generate some heat. So we've got the kinetic energy, 1/2 mv squared, plus the potential energy. That's going to be the diameter of this thing, 0.2 meters, mg and h. The heat generated is going to be just that frictional force times the distance that it moves. You have to do a little geometry here. I think you can handle that. We just need to get the length of this hypotenuse. That length times the sine of 25 has got to be 0.5. And so this length here turned out to be 1.184, this number of meters. Okay? Then we can set the initial energy equal to the final energy. And when we do that, we have all these numbers except for the velocity. We can get the velocity up on top. So that tells us how fast it's traveling. Then, so we got that from energy principles, and that's often what we'll do. And then we can turn over to force methods and take a look at this. We've got the idea of the beads going around here. We've got some forces. Now, it's riding on the wire. It is possible that as it goes in the wire, if it's going really fast, there's going to be a tendency the bead wants to fly off on a straight line. The wire is going to be pushing on the bottom of the hole of the bead in the negative, and that's actually what's going to happen. I'm playing the game here as if it was traveling really slow, or if it's just sitting up on top. Then the bead would sit on the wire here, and the wire would provide a normal force up. So is the normal force down or is it up? I wanted to show that it really doesn't matter what it is. You can solve for that. What I did is just say, I'm going to play with it here. I'm just going to call up is the normal force. So it's kind of sitting on the wire like this. It's going slowly enough. It's just riding on the top of it. mg, of course, still points down. We've got the velocity. And so it should be traveling in a circular path. So the sum of the forces in the radial direction here, I'm calling into the center positive, would be mg. I'm having it minus the normal force, and then that has to be equal to mv squared over r. So I had, and I have v. Actually, I had v squared. It would have been expedient just to put in v squared here, but 1/2 v squared over r. And then I can solve for the normal force. He wants to find what is the magnitude and direction of the normal force. And I go ahead and solve for this, and solving for n. You can follow my math. But I get a negative answer. This negative just implies that my chosen direction for the normal force, I said it goes up, was actually pointed down in the negative of that. So it turns out it's more going to be, this is going to be the picture. Now, maybe you guessed this to begin with. You could go ahead and do that. But the bottom line is the math is going to work out. It's going to tell you whether it is plus the way you wanted it or minus what was pointing in. And so this is what he's looking for. What is the magnitude and now the direction? Normal force, and it points down.
Yeah, so the normal force is the magnitude.
Yeah.
It's not always true though, right?
Oh, the normal force is the magnitude of that. So many newtons. And as far as the direction we need to determine mathematically.
But I mean, in a problem like this, isn't the normal force always the magnitude?
It's asking for the magnitude.
Well, the magnitude and direction. There's also a direction associated with this. Now, I don't have to get anything fancy. I just said it points down, so if you want to call it in the y-hat direction or negative. Okay, I think I'll leave this. This is kind of another thing. This is one of the problems where you have a kid sliding down the slide. This one might be a good one just to kind of leave you with. I think you can do this. Where we get the energy here, he wants to, what is he looking for here? Fraction. Okay, so the kid is going to start here, is coming down the slide, and has the shape of the quarter circle. When the child is 1.5 meters above the ground, what is the force, magnitude, and direction of the slide? So this would be one that you typically would solve for the magnitude and direction of the normal force. Normal force should be directed into the center of the curve. Okay, I think I'll leave you with that since we're kind of over time here.
Does the child stop?
Oh, I think the kid is just on their way down, and when the kid is on the way down, when he happens to be here, when the child is above the ground, what force, magnitude, and direction does the slide exhibit on the child? So that would be the normal force. There's no frictional force. There is mg, and this is kind of a bad picture, but the normal force pointing in, mg pointing down.
They're not even worried about the very bottom of the slide.
Right, he's not asking about that. So anyway, just another example of energy methods and force methods. So, woo, okay, good luck. Okay, we went a little long, but okay, so good luck. Good luck. I guess it's Wednesday. You got some time to get that together.
Yeah, but mine's pretty complex. So,
Yeah.